we demonstrate Platypus, a sub-millimeter micro-displacement sensing system based on mmWave radars and passive tags. Micro-displacement measurement is a crucial task in industrial systems and civil structures. For example, in structural health monitoring, millimeter-level displacement of specific points in the structure can create deformation and potentially lead to collapse. Prior arts which use either traditional sensors, RFID, vision-based systems, or advanced surveying platforms suffers from limited accuracy, prohibitive costs, lacking robustness, or short range. More recent solutions based on radars partially address these challenges by tracking the phase change of the object of interest reflection. For millimeter wave radars, millimeter-level displacements create a large phase change. However, hardware imperfection or dynamic objects in the background create noises, masking the phase caused by the micro-displacements and drastically drop accuracy. Platypus approaches the problem by attaching passive millimeter wave tags to points of interest on the structure. By leveraging properties of the tag, Platypus achieves simultaneous detection of multiple points, robustness to dynamic environment, and sub-millimeter level accuracy. To achieve this, the tag switches between reflecting and terminating the RF signal, which appears as a sync signature in the range Doppler profile. While the noise still exists in the DC bin of the Doppler FFT, the signature that exists in a different FFT bin acts as the phase carrier, separating phase caused by the micro-displacement from noise. We also leverage the FFT property of bin leakage and utilize the phase information of all affected range bins. In addition, we split the signature into I and Q components, which contains much more peaks and facilitates phase change detection in adjacent sample frames. In a demo, we mount the tag on a stepper motor-driven motion stage and create different displacement patterns such as linear or sinusoidal. Platypus can precisely track microdisplacements without making any assumption about the displacement pattern or direction. We demonstrate robustness to multipath by having extra stationary and moving corner reflectors. We also demonstrate performance under wood occlusion. Note that small phase unwrapping issues still exist because of the short time window in live processing. We also test for cardboard occlusions. Note how the occlusion is placed closely in front of the tag to block all possible multipath routes. To learn more about our research, check out our paper in IPSN 2023.